Okay, so good afternoon, everyone. So today I'm going to present the latest findings and the work to do on the project that I'm doing as part of my PhD, supervised here by Professor Manuel Sanjurjo. So the main topic is the application of deep learning techniques, mainly for optical navigation in various solar system exploration missions. So getting right into it, I wanted to start with the concept of computer vision for navigation. So the current state-of-the-art monocular vision methods for space mission, they currently rely on basically identifying a predefined set of landmarks or surface features in the image and perform a matching with those landmarks. So there are two main problems with these algorithms, which is that there are a lot of limitations in adverse illumination conditions in terms of robustness and performance. And also the performance is limited because due to the large number of hypotheses that has to be tested when matching these landmarks, which should be identified in the image. So the main goal of the project is to substitute these feature matching algorithms by convolutional neural network or other deep learning algorithms for optical navigation, such that we provide an input to the image and the network directly provides the spacecraft pose, so the three coordinates for the position and the three Euler angles. So as I said, the main goal is to apply deep learning for this problem. So the project would consist on training neural networks, which will directly learn the transformation between a grayscale image, so a 2D space, to the spacecraft pose vector, so the 6D space. But of course, there are a few challenges in doing so. So first, that the convolutional neural network would act sort of like a black box. So we don't really know what's happening inside, so we have to perform extensive testing and validation to identify possible failure cases of these convolutional neural networks that we develop. And also it's very well known that machine learning applications require a very large amount of data, which for space missions sometimes is not the case. So for example, we started working for a mission to a minor body, so we focused on Churyumov-Gerasimenko comet, the one that was visited by a Rosetta mission. So for comets and asteroids, we have few space missions like Osiris-Rex, Hayabusa from JAXA, Rosetta, of course, but still the data sets are very limited, just a few thousand images, and of course those images are limited by geometric conditions of those missions, so we cannot use directly those to get a general solution. So we have to deal with that as well, and also another challenge, which is what we call generalization of the machine learning solution, which is basically that we want the neural networks that we develop to work for the wider range of possible use cases. And more specifically, we want to fill the gap between using synthetic images for training and using real images, which is in the end what the network will be having in a real mission. So in order to address these challenges, we have two main tasks to address. So the first one is to develop tools for generating these synthetic images that I mentioned to solve this problem that we don't have enough data for training. So for doing so, we are using mainly two methods. So we are using both state-of-the-art graphical rendering software like Blender, which is free and it's very well known for rendering, and Unity, which was originally designed for video game design, but it's more and more used in industry. But also we have developed our own open source Python package for GPU accelerated rendering, which is also open source. And then once we have these synthetic sets of images for training, we have, of course, to design and train the neural networks, which should be capable of solving this spacecraft pose estimation problem. So we are mainly working on Python with TensorFlow environment. So in this context, we have to deal with designing the architecture of the network itself. So we are dealing with state-of-the-art architectures like AlexNet, Inception, ResNet, or the more lighter MobileNet, and also small variations of these networks. And also we have to work with what we call training configuration, which is basically the parameters, the techniques that you have to apply during training the neural networks to get the optimal solution. So for example, we have to select the proper loss function, which is the function that we use for adjusting the weights in the network, also the activation functions of the different layers in the network, also classification versus regression approach, which we'll talk a bit more later on, also data augmentation techniques to say extend even further the data sets that we have, so regularization techniques and these sort of things. So starting with the synthetic image generation, so as I said, we started with the case of the comet, so a mission to a minor body. So for this, we developed SpyRender, which is an open source Python package for GPU accelerated rendering. So it's capable of very efficiently rendering very large sets of images, which are suitable for training the neural networks that we have used. So it can take two types of inputs. So first, it can ingest a user-defined list of random ranges. So basically, if we want to get images only from a range of positions, we would define those ranges, and the package will produce images just within those ranges, but random. So the network is able to work with any images which is within those ranges. This, of course, is more suitable for training. And then we have also a second mode in which the geometry of the objects in the scene, which is rendered, is directly took from the SPICE toolkit. So this is more suitable for generating validation sets. So for example, for generating a sequence of synthetic images corresponding to a real mission like Rosetta or any other mission. So we have produced mainly two types of sets. So the first one is suitable for global estimation, global precision estimation. So it consists on positions covering the whole 3D space around the target. And we have also produced a second group which consists on local or regional sets. So each set contains only images from a specified range around the 3D space of the target. So after playing around a bit, we found that a discretization of about 32 sectors worked pretty well with the classification network that I will introduce after. So that was for the first project that we worked on, which was for position estimation in the vicinity of a minor body, which I will show a bit later the results of the training. But as we are already working with extending this project to other type of missions, so I just wanted to introduce another method, which consists on a combination of different techniques. So we, for an Earth observation mission, which is like OPSAT, which is a small CubeSat, which is owned by ESOC, by the European Space Agency, and it's orbiting the Earth, but unlikely they don't have GPS working. So they have images, but they don't really know the label of the images. So this would be one case in which in this neural network would be very helpful for them. So for generating this kind of synthetic images for an Earth observation mission, we use Google Earth Engine, which is it's also a free platform in which you have access to almost any Earth observation dataset that you can imagine for surface elevation, surface reflectance, chemical composition, so pretty a lot of different datasets, so it's really interesting to play around with that. So specifically, we combine the data from the shuttle radar mission for elevation data, and also the Sentinel-2 mission for the surface albedo. So combining these two sets, we can create very high detail and also very large 3D model of the Earth, which contains the surface elevation, but also it contains the surface albedo. And consider that the Sentinel-2 passes over every point of the Earth every 2 weeks. We are able also to produce seasonal models, so we can also train the network to deal with seasonal changes. So, of course, ingesting this high-detail 3D model into Blender or other rendering software, so we can introduce also other effects, like, for example, the light scattering of the atmosphere, which we didn't have in the minor body mission. Also, we can deal with clouds, because, of course, in the comet you don't have clouds. So modeling these different effects, we can get to a synthetic image which pretty much assembles the real one from OPSAT. And with this, we'll be able to train the neural network which will be able to work with the real images as well. So going back a bit to the first case, which was for the Comet mission. I wanted to introduce the data augmentation concept, which is very important for us. So this, as I mentioned before, consists on extending the data set that we have. So the network is able to deal with all these different image effects. So for example, in the case of this mission, we have, of course, a scale variation as the spacecraft moves closer or farther from the comet, viewpoint variation, of course, depending on the position of the camera, illumination conditions, so not only intensity, but also the direction of the illumination source, which, especially for a complex, say, body like Churyumov-Gerasimenko, so from the image on the bottom left, you can see that the three images are taken with the same viewpoint, just changing the illumination direction, and the target looks completely different. So the idea is that we applied all these effects, so rotation, scale, variation, also Gaussian noise to model distortions in the image, which are very likely in this type of space missions, but also to model other type of phenomena like the dust, which is ejected by the comet when it's closer to the sun. So modeling all this, the network is able to deal with all these effects, which are present in the real images. So about the neural network architecture, as I mentioned, so we are using a slightly simpler model as AlexNet. So it consists on 2 convolutional layers followed by 3 fully connected layers, the last one being the output layer. So we use nonlinear activation function. We use the rectified linear unit, which is almost linear but still nonlinear, which helps avoiding the vanishing gradient problem, but still aids the network to be able to deal with nonlinearities, which are present in the data which the network has to deal with. And as a regularization technique, which is basically avoid the network to learn too much the train set and forget about other type of images which are not in the train set. So we use a dropout rate of 25%, which means that at every training epoch, we are dropping 25% of the weights. So the network has to learn again those weights at the next iteration, and it's a very typical way to prevent overfitting. So then about classification or regression approach. So in this case of in these cases of estimation, we can take 2 approaches. So the first one being multi-class classification. To simplify this a bit, would be like a classification network for clothing. So you provide an image of whatever piece of clothing, and the network will say, okay, it's pants, it's shirts, it's shoes, whatever. So this is exactly the same, but for position. So we will provide an image of the target, and the network has to tell us, okay, we are in this region of the target. Of course, the problem is that the level of accuracy of the classification directly depends on the level of discretization, but also the larger is the number of labels, so the larger is the discretization, the larger is the estimation error, because it's more difficult for the network to distinguish between those sectors. So we have a second approach, which is regression. So it's basically the output, it's a continuous variable, which in this case it's the 3 coordinates for the position and the 3 Euler angles. But using this approach, the main problem is that it's very difficult to train a single regression network, which is capable of global position estimation around the target, simply because target looks very different from one viewpoint or from another. However, regression shows much better accuracy in regional sets. So these findings led to what we call an hybrid approach. So we use a 2 levels neural network. So we have a high level, which is a multi-class classification network, which will estimate the sector of the 3D space around the target, and provided the output of this classification network, the image will be sent to a second low-level regression network. So we have a set of low-level regression networks, each trained just for one specific sector of the 3D space. And this low-level regression network is able to estimate accurately the position and also the roll angle around the camera. So we, at the later stage of the design, we added a high-level regression for the shifting, which is a prior step in which we basically center the target in the image, which, as you will see later, substantially boosted the performance of the classification network, but also it provides kind of the pitch and yaw angles in terms of a nadir pointed reference frame. So these are some summary of the results that we have. So on the left, it's the classification network training. So we have trained the network, so the number of times that we update the weights of the network until we get convergence of the loss function at the top left. Basically, we started with the simplest case in which we have only random variation of the illumination source. Okay, yeah. And then we started adding other effects like random roll, brightness, offset, Gaussian noise, and as you can see, with 10 pixels offset or 70 pixels offset, the boost in performance is about 40% in the classification, in the accuracy. So it's a bit difficult to see it, but yeah. That's why we introduced the shifting neural network. And then for the low-level regression, we have an error of less than 6 kilometers for a more than 100 kilometers orbit. And for the roll angle, so the angle of, on the plane of the detector of the camera, which is less than 20 degrees. So some of the achievements that we have presented our work in the International Astronautical Congress in Dubai last October. We have submitted a paper to the Transactions in Aerospace and Electronics about applying these neural networks for the case of the minor body mission. And also we have an abstract accepted for the International Astronautical Congress this year about what we call CAMNet, which is same approach but for the Earth observation mission. And then about work to be done. So we have to train for the Earth observation mission. We already have these photorealistic images, but we have to configure the training. More specifically, trying to fix this, to fill this gap between synthetic and real training, so we will be able to test the network in a real mission, which is right now orbiting the Earth. Also, we want to test other deep learning approaches, like using a recurrent neural network to take account a sequence of images instead of a single image. And also extend the project to other missions, like for the Moon, Mars, and Mercury, for which we also have data sets which will allow us to produce synthetic images. And yeah, that's all. So if there's any question.
Thank you, Alfredo.
Sorry for running late.